Hello everyone, this is Prakash Kumar, and in this video I am going to explain how to simulate a file in OpenFOAM and generate meaningful graph using online spreadsheets like provided by Google. So for simulation I am going to use the default tutorial called Wing Motion in OpenFOAM. I will open it in the editing software. For that purpose I will use the VS Code. So this is how the file looks like in VS Code. There are three main folders called the snappy hex mesh, a steady case, and a transient case. First, we'll begin with the snappy hex mesh. It has two folders, constant and system. I'll run this through my terminal. First, we'll go inside the snappy hex mesh folder. We will use the block mesh command to mesh the background of the tutorial case. After meshing the background, we'll use the snappy hex mesh tool for providing a cutout of a wing for mesh. It says the mesh has successfully finished without any error. So I can view the mesh generated in the paraview window. I will directly move to the folder where I was working for viewing the result. As you can see, this is the mesh generated after using the snappy hex mesh dictionary. There is a very smooth transition from the coarse mesh around the boundary to a very fine mesh near the wing structure. This is due to the reason there will be more morphing very close to the wing compared to insignificant movement very far away from the wing. Additionally, the downstream region of the wing is very fine so that we can record more accurately in those regions without consuming much of our time. Next, we will move on to the steady flow simulation. In steady flow, I have three folders, namely 0, constant, and system. I'll move back to my terminal where I'll direct directly to the steady folder. The first command that I will use is extrude mesh. Next, I'll create a patch and then we'll run the simulation using the foam run command. My simulation will run till 3000 iteration as given in my command dict. As you can see, after 3000 seconds, my simulation has stopped with giving me the steady flow end value. Now I will use it as the initial case for my transient flow. For that, I'll move back to the transient folder. I will also show you the result generated after the steady flow simulation using the paraview. As you can see, there are 30 files being generated at the interval of 100 till 3000 from the simulation that I have done. The result can be seen in the control deck file. So this is the final result of the steady flow. It started like this and ended at the 3000th iteration. I will use the final data as the input of the transient file. There's an important file in the wing motion tutorial that is called the all run, which we can directly use to run all the three folders simultaneously. I'll use it for taking the commands out of it. The map field command is used to directly take the result from steady case end time to the initial time of the transient case. As you can see, it has interpolated the pressure, velocity, mu, omega, and k value. After this, we are going to use the parallelism in OpenFOAM. For that, I will be editing the decompose dict of OpenFOAM. The number of processor in my computer is 6, so I will set the number of subdomains as 6 and set the simple coefficients as 3, 2, and 1 respectively in the x, y, and z direction. For running it, I'll use the command decompose pair. It created the 6 processors for running the application. For running it in parallel, I'll use the command mpi run like this. It will generate me a result of C, coefficient of moment, coefficient of drag, and coefficient of lift, including coefficient of lift at front and coefficient of lift at the rear of the wing. This data is very useful because I can directly copy it to the spreadsheet and generate graph through it. I'll copy this data up and put it in the Google spreadsheet. As you can see, I have copied the data from the file generated to the Google spreadsheet. From the data of C, coefficient of lift and coefficient of drag with respect to time, I have generated two different graphs. First is the drag coefficient with time, and second is the lift coefficient with time. As you can see, as the angle of attack increases, my coefficient of lift value also increases. At a particular point, it becomes stable, and after that, with the decrease in the angle of attack, the coefficient of lift decreases. The same trend is followed for the drag coefficient. So this is how you can use the value generated in OpenFOAM to generate meaningful graph and do the analysis of a airfoil.